everyone, thanks so much for joining this video. Today we're going to be learning about the equilibrium constant Kc for homogeneous systems. So we're going to learn about what the expression means, how we calculate it, and we're going to construct the expression for Kc to calculate a value of Kc for a specific experiment, and then we're going to learn how to predict the qualitative effects of changes of temperature on the value of Kc. So Kc is called the equilibrium constant, and how we work it out is basically the Kc is the ratio between the concentration of products and the concentration of reactants. So if we divide the concentration of products by the concentration of reactants, then we find this constant called Kc. So all reactions can be written in this form, where the small letters are the number of moles, and the bigger letters are the reactants, or the products in this case. So X, Y, and Z are all products for the forward reaction anyway, and then A, B, and C are the reactants for the forward product. And then what we can do is find out this ratio at the bottom. Basically, it's the same as the concentration of the product over the concentration over the reactant, but this is for a more general reaction. So when we actually work out this ratio, it actually comes out as a constant figure. If we repeat this reaction lots and lots of times and work out this ratio again and again, we should get the same value, a constant. And this constant is what we call Kc. So that is the equilibrium constant. And a really important point about the equilibrium constant Kc is that it's only affected by temperature. So changing the pressure or adding a catalyst or changing the concentrations won't have any effect onto the Kc. So now we're going to discuss how to work out the Kc of a reaction. The simplest Kc calculation questions actually give you the equilibrium quantities already in the question. So the equilibrium quantities are basically how much of everything there is when it is in equilibrium. So calculate the Kc for the following equilibrium given the results of an analysis of the equilibrium mixture, which show that the concentration of SO2 equals 0.230 moles per decimeter cubed. Oxygen is 1.370 moles per decimeter cubed, and SO3 is 0.920 moles per decimeter cubed. So what we do is we simply just plug it into the equation. So we have Kc equals X at equilibrium multiplied by X, and then we have A, which is at equilibrium, the concentration of A, and we multiply it by how many moles of it we have, and then we multiply that by the concentration of B, and times it by how many moles of it we have. So if we call this A, this B, and this X, we should be able to find this. So that means we're finding the concentration of SO3 at equilibrium and then multiplying it by 2 because this is the amount of moles of SO3 we have. And then on the bottom we'll have SO2, the concentration of it at equilibrium, and multiply that by how many moles of it we have, and then multiply that by the concentration of oxygen taken at equilibrium, and the moles of that is just 1, so there's no power. So it's really important to remember that Kc measures the ratio with the products at the top, because if you did this fraction the other way around, it wouldn't work. So using these values that they've given us for the equilibrium mixture concentrations, we can then work out Kc. So we have 0.920 squared over 0.230 squared times by 1.370. And that gives us 11.7. Now, the thing with KC is that the units of it change depending on the reaction. So the way we work out the units is that we use the formula that we have here, but we cancel out some of the units. So for example, for this example, on the top we have a concentration squared. So we have moles per decimeters cubed squared. And then on the bottom, we have another moles per decimeters cubed squared and just a normal moles per decimeters cubed. And so then we cancel. So I know that I can cancel this with this. And then we're just left with 1 over a mole per decimeters cubed. And so the units for this case C are mole to the minus 1 and then decimeters cubed, because we have 1 over a mole per decimeters cubed. I've also rounded it to 3 significant figures because in the question everything is has been rounded to 3 significant figures. So that's what gives us a clue as to what to round the answer to. Harder questions will require you to find the equilibrium quantities yourself first. So I've bullet pointed how to work out equilibrium quantities. So again, equilibrium quantities are just the moles that we have of each species in the equilibrium mixture. And the question should always give you the starting moles of each species and at least one of the equilibrium moles of either the reactants or the products in equilibrium. So first what you do is write out the equation, and then you write down the initial moles of each species, and then you work out the change in moles for the known species, so the one that you're given the starting moles and the equilibrium moles, and then you determine the change in moles for the other species using the ratio between the known one and the unknown ones. And then we can work out the equilibrium moles of all of them. A really important note is that if the moles of a species has increased on one side, so say the moles of the reactants has increased, that means that the moles of the products will decrease. So we're going to look at this example, telling us to work out the number of moles of each species present at equilibrium for the following reaction, given that we mix 2 moles of A with 1 mole of B, and an equilibrium is established which contains 0.4 moles of B. So the first thing I do is write down the equation. So we have A plus 3B forms 2C plus D. And then I write down the moles that they initially have, so the moles that we've reacted together. So in the question we have 2 moles of A, and then we have 1 mole of B, and then it doesn't mention C or D, so that means that we assume that they start off as 0. And these are the initial moles. And then what we do is we write down the equilibrium mole that we do know, which is the 0.4 moles of B. So this is equilibrium moles. And then we can work out how many moles have been lost of B during the process to get to equilibrium. And so 1 minus 0.4 is 0.6. So we've lost 0.6 moles of B. So how do we find how many moles we've lost of A? Well, we use the ratio between A and B. So the ratio is 1 to 3. So that means if we've lost 0.6 moles of B, then that means that we've lost 0.2 moles of A. So this would be minus 0.2, and so the equilibrium moles of A would be 1.8. And then you do the same on the other side. However, you need to remember that if the reactants lose moles, then that means that the products will gain moles. And the other way around, if the reactants gain moles, then the products will lose moles. So you do the same thing with the ratios. So now you look at the ratio between B and C. So I can see that I've got a 3:2 ratio. So I have a 3:2 ratio, and B loses 0.6, and so C should gain 0.4 moles. And with D, it should gain 0.2 moles because it's a 3:1 ratio again between B and D. So I gain 0.2 moles, and so C will be 0.4 and D will be 0.2. And now we've found out the equilibrium moles. We can then apply this to finding Kc by converting the moles to concentrations. So now we can find out how to work out the Kc of a reaction without the equilibrium moles. So if we look at this example, 200 grams of ethyl ethanoate and 7 grams of water were refluxed together. At equilibrium, the mixture contained 0.250 moles of ethanoic acid. Calculate Kc for the hydrolysis of ethyl ethanoate. So here we have the equation. So the first thing I'm going to do is work out the original moles of ethyl ethanoate and water. So we have the equation moles equals mass over mR. So we can work out the moles of this. So the moles of CH3COO CH2CH3 is equal to 200 grams divided by its MR, which comes out to be 88, and that's by doing adding up all the separate ARs. So we've got 12 for carbon, 1 for hydrogen, 16 for the oxygens, and that comes out to be 2.27 moles. And then we do the same with water. So we have the moles of water is equal to 7 grams divided by the MR of water, which is 18 because it's 16 plus 2. And that comes out to be 0.389 moles. And so now we can work out the equilibrium moles. So you write out the equation. And then we put in these moles. So we have 2.27 of this one and 0.389 of the water. So this is initial moles. And then we have, we assume that we have 0 of these. Probably 2 3 significant figures because everything else looks like it's in 3 significant figures. And then we put in our known equilibrium mole, which is this 0.250 mole of ethanoic acid. Ethanoic acid is the CH3COOH, so we have 0.250 moles of this. And so now we can begin working out how much we've lost. So here we have gained 0.250 moles. And so that means that looking at the ratio between these two, it's a 1-to-1 ratio, which means that this one must have also increased by 0.250 moles. And then we see that actually the ratio between everything and this ethanoic acid is 1-to-1. So that means that the reactants have both lost 0.250 moles. And so we have that the equilibrium moles are 2.02, 0.139, and 0.250, and these are the equilibrium moles. So then we can use these to now find Kc. Because Kc is just a ratio, that means that we actually don't need to convert the equilibrium moles into concentrations, because if we do that, we'll actually get the same thing. So we can just work out Kc just using the moles. So Kc equals the moles of CH3COH and CH3CH2OH. So that'll be 0.250 times 0.250, and then we divide that by 2.02 times 0.139, and that comes out to be 0.22. And now we have a look at the units again. So we have moles squared per decimeter to the -6 because we've got two of them, and we've got the same on the bottom. So what that means is that they cancel out, and Kc actually has no units for this example. And another thing is that the Kc can be calculated using just the moles because the volumes will be the same, because we work out concentration equals moles over volume. So if we're using the same volume, then that means that all the volumes actually cancel out, because we'll have mole squared over volume squared over mole squared over volume squared. So these two volume squared, if they're the same value, they'll just cancel out. So actually using just the moles for this Kc will be fine. So now we're going to look at some questions. The first one says that the equilibrium below was established by allowing 2 moles of ethanol and 1 mole of ethanoic acid to react at 25 degrees. At equilibrium, the mixture contained 0.845 moles of ethyl ethanoate. Calculate Kc at this temperature. So I'm just going to use the equation given. I'm not going to write it out again. But we first start off with writing the initial moles, which have been given to us in the questions, so we don't actually need to work them out. So we have 2 moles of ethanol, so we have 2 moles, and 1 mole of ethanoic acid. And the products aren't mentioned, so that means that we assume they're 0. And now we look at the difference. So we know that 0.845 moles of ethyl ethanoate was in the equilibrium mixture. So we have 0.845 of this in the equilibrium mixture. And so the difference here is that it's gained 0.845 moles. And now we have a look at the ratios between this ethyl ethanoate and everything else. And it looks as though it's a 1-to-1 ratio for everything. So that makes our job quite simple. So the products all gain 0.845 moles, and all the reactants lose 0.845 moles. So again, a really important thing to remember is that if the reactants lose moles, then the products gain moles, and vice versa. So it's always the opposite. And so we have 0.845 moles of this water. We have 0.155 moles of this ethanoic acid, and we have 1.155 moles of the ethanol. And so these are our equilibrium moles. Now, because everything's going together, we have the same volume. That means that we can just use Kc with the moles instead of the concentrations. And so working out the Kc, would be Kc equals the moles of the ethyl ethanoate times by the moles of water divided by the moles of ethanoic acid and the moles of ethanol. And so we have 0.845 times by 0.845 divided by 0.155 times 1.155, which comes out to be 3.99. And I've rounded this to three significant figures again because the values in the question originally are three significant figures. And also the units for Kc for this reaction. How to work that out would be to just write it out. So we've got 2 moles per decimeters cubed on the top, and then divided by 2 on the bottom. So that means that everything cancels out. So there are no units again for this question. So this question is slightly different because we're actually given the Kc, but we're told to work out the equilibrium concentration of one of the reactants. So feel free to pause the video and try it out yourself first, or you can follow along. So in the following equilibrium, Kc equals 54.1 at a particular temperature. The equilibrium mixture was found to contain hydrogen at a concentration of 0.480 times 10 to the minus 3 moles per decimeters cubed, and hydrogen iodide at a concentration of 3.53 times 10 to the minus 3 moles per decimeters cubed. A asks us, what is the equilibrium concentration of iodine? And so we don't actually need to work out the equilibrium moles because they've already told us them. So we have 0.480 times 10 to the minus 3 moles per decimeters cubed of hydrogen, and 3.53 times 10 to the minus 3 moles per decimeters cubed of the hydrogen iodide. And so using the Kc equation, we can then work out the equilibrium concentration of I2. So we have that Kc equals the concentration of Hi taken at equilibrium squared divided by the concentration of hydrogen at equilibrium times by the concentration of iodine at equilibrium. And so if we rearrange this formula, then we can find this equilibrium concentration of the iodine. And so the equilibrium concentration of iodine is equal to the concentration of hydrogen iodide squared at equilibrium divided by Kc times by the concentration of hydrogen at equilibrium. And that comes out to be 3.53 times 10 to the minus 3 squared divided by the Kc, which is 54.1, times by 0.480 times 10 to the minus 3. And this comes out to be 4.80 times 10 to the minus 4. And I've also rounded that to three significant figures because everything else in the question is. So for B, what effect would doubling the concentration of hydrogen have on the equilibrium position in Kc? So if we have a look at the equation, if we doubled the concentration of hydrogen by Le Chatelier's principle, the equilibrium would move to counteract that change. So try to decrease the concentration of hydrogen. And the way it does that is to produce more products. And so the equilibrium shifts to the right. And the thing to remember about Kc is that it is not affected by concentration. So the Kc remains at 54.1. For C, what effect would increasing the temperature have on the equilibrium and Kc? So when we increase the temperature, the equilibrium acts to decrease the temperature, so it favours an endothermic reaction. So looking at this bit here, it says that the delta H is bigger than 0, which means that the forward reaction is actually endothermic because it's positive. It's got positive enthalpy change. And so that means that when we increase the temperature, the equilibrium will favour the endothermic reaction, which is the forward reaction, and so the equilibrium shifts to the right. And what happens to the Kc is that because the Kc is the ratio of products to reactants with the products on top, that means that if we produce more products, that means that fraction will be a lot bigger. So Kc actually increases. Because Kc is the concentration of products over the concentration of reactants. So if this has increased, the product has increased, that means that this whole fraction will be a lot bigger. So the Kc has increased. Hi everyone, thanks so much for joining this video. Today we're going to look at some harder questions for working out Kc. So the first question is, when 1 mole of steam and 1 mole of carbon monoxide were allowed to reach equilibrium, 33.3% of the equilibrium volume is hydrogen. Calculate Kc at this temperature. And so first I can write the initial moles. So I have 1 of water and 1 of the carbon monoxide, and then 0 of both hydrogen and carbon dioxide because they're not mentioned in the question. And then we're told that 33.3% of the equilibrium volume is hydrogen, and 33.3% is equal to 1/3. So we know that 1/3 of the whole entire equilibrium volume is made out of hydrogen. So if we call this X, because we don't know how much volume there is total, so we actually don't know what the equilibrium moles of hydrogen are. So if we call the hydrogen X, so it's changed by an X amount, then we look at the ratios. So actually all the ratios are 1:1. So that means that carbon dioxide increases by X as well. And the carbon monoxide decreases by X. So that means that the equilibrium moles will be 1 minus X. And for water, it'll be the same. So these are the equilibrium moles. And so if we add all of these up, that actually tells us the whole equilibrium volume. So we have equilibrium volume is equal to 1 minus X plus 1 minus X plus X plus X, which equals 2. So the whole equilibrium volume is 2. And we know that 1/3 of the whole equilibrium volume is hydrogen. So we know that 1/3 is equal to X over 2. And so rearranging that gives us X. So now we know that X equals 2/3. So we know all the values for the equilibrium moles. So we have 2/3 of hydrogen, 2/3 of carbon dioxide, and then we have 1 minus 2/3, which is 1/3 of carbon monoxide, and 1/3 of water. And so now we can work out the Kc. So Kc is equal to the moles of this added together with the mole of this, times by the mole of this, and then divided by the moles of carbon monoxide times by the moles of water. So we have 2/3 times by 2/3 over 1/3 times 1/3. And that comes out to be 4. And the units for Kc will be moles squared decimeter to the -6 over mole squared to decimeter -6. So these will cancel, so there are no units. Before we move on to the second question, feel free to click off the video and try it for yourself first. So Kc for the equilibrium below is 10 at 450 Kelvin. If 1 mole of the ester is mixed with 5 moles of water and the mixture allowed to reach equilibrium, how many moles of each species will be present at equilibrium? So the first thing I do again is to write out the equation. And then write out the initial moles that we already know. So we know 1 mole of ester is mixed with 5 moles of water. So we have 1 here and 5 here, and then 0 of these two. So these are initial moles. And then we actually don't know. We haven't been told how many equilibrium moles we have of one of the species, so we just have to label it X. So first I'm going to label what we're adding and what we're subtracting. So let's say, well, because the products start off at 0, that means they can't lose moles, they have to gain. So that means on the right hand side we must have pluses. So let's say this is plus X and this is also plus X. That means that the reactants are minus X and minus X because everything is a 1-to-1 ratio. And so we can write out expressions for the equilibrium moles. So we have 1 minus X and 5 minus X, X and X, and these are the equilibrium moles. Now we use the Kc equation to find out what X is. So Kc is equal to the moles of this times by the moles of this over the moles of this times by this. So we would have X times by X over 1 minus X times by 5 minus X. And we know that the Kc is 10, so that all equals 10. And so we form a quadratic equation. So we have X squared equals 10 times by, and this, I'm just going to expand the bracket, so we have 5 minus 6x plus x squared. And then we'll have 9x squared minus 60x plus 50 equals 0. So then we plug that into the quadratic equation. So we get x equals minus b plus or minus b squared minus 4ac over 2a, which is minus 60 plus or minus square root of minus 60 squared minus 4 times 9 times 50 all over 2 times 9. And this gives us x equals 5.69 or x equals 0.976. And now we have to decide which one we use. And so looking back at our equilibrium moles, we can't really have 5.69 because that means that this and this would be negative, and we can't have negative moles. So this means that we must have to have X equals 0.976. And so now we found the equilibrium moles of all of the species just by plugging in the X to our expressions. So we have the equilibrium moles. So we have the ester will be equal to 1 minus 0.976, which is 0.024. And then we have water, which is equal to 5 minus 0.976, which is equal to 4.024. And then we have HCOOCH, which will be equal to 0.976. And then also we have the methanol, which will also be 0.976. And those are our equilibrium moles.